Hello.
Hello.
Howdy.
Hi, Jim. thanks
Hi.
for thanks for chatting with me. I appreciate it.
Sure.
Yeah. So I suppose my first question, I actually kind of wanted to start off a little bit general. So I'm
Yeah.
curious, why is it important to continue to send probes to Mars?
Well, Mars is a big place, and it's really a rather tricky place. It's beguiled us ever since we sent our first spacecraft by the planet. And so, as we start to piece together the information to understand this world, a place where we can reasonably ask, could there have been a record of past life? We need to bring all the information together to pose that question in an informed way. It's a huge planet, 150 million square kilometers of surface area, a big atmosphere, rarefied, polar caps, climate change, all the right stuff. And so where do you start? Where do you attack that planet? So what we've done is build a program, a campaign, if you will, to study Mars through science and exploration tools. Maven's a piece of that. Curiosity's a piece of that. This was our plan when we redesigned the Mars program in 2000 to capture the big Mars, so we wouldn't be fooled again.
hmm Great. And then why specifically is it important to look at the Martian atmosphere the way that Maven will?
Well, the Martian atmosphere is a critical piece of the puzzle of how Mars works. Certainly Mars was born with a different atmosphere than we think we see today. But we need to measure the atmosphere of today, how it works, how it's lost to space, how it interacts with the solar wind, how that relates to the chemistry of the rocks on the surface that we're measuring with Curiosity, we've measured with Spirit and Opportunity. All that is part of this big ensemble of information we need to really understand how Mars works. If we're going to ask, is there a record of past life on Mars? Could Mars have been alive? Is it still alive? We need to do that fundamental work. The atmosphere is part of that equation. And today, we really haven't done a lot of work on that. So Maven is going to fill in a lot of the gaps that we've known we needed to fill in since the late 1970s.
Huh. Yeah, and sort of speaking to those gaps, what is how do scientists think that Mars lost its atmosphere? I guess what's the theory that we're sort of going off of?
Well, there's several theories. I mean, there's a theory that says that Mars' atmosphere was born as a big system like early Earth's. It was then blown off by tremendous impacts, those that formed the giant basins like Hellas and Argyre. And then a new atmosphere evolved from volcanic outgassing. That's one model, one theory. And then that atmosphere has subsequently changed through the action of geology and activity from space as it's been space weathered away. And so that's one question. Mars is a smaller planet. It's easier for it to lose pieces of its atmosphere to space because we think we understand that process here on Earth pretty well. Another theory says the Mars atmosphere has been fundamentally modified by the action of geology and possibly even biological activity. So that's another question, and that's important to ask. Two end members. Another theory says the Mars atmosphere is a big chemistry lab, and it's slowly freezing out and being re-released over the climate cycles of Mars, the annual cycles. We don't know how to distinguish those. Maven to the rescue to fill in some of the gaps, literally. Fill in the gaps, do that chemistry experiment the right way, get a big A on your report card, and allow us to distinguish between those theories. And then connect those to what we're seeing in the rock record with Curiosity.
Wow. Okay. Yeah. So there is some kind of collaboration between the rovers on Mars and Maven and like MRO. So I'm curious. So Maven will actually have some communications capabilities to be able to send data from Mars, even sent up by Curiosity. Is that correct?
Absolutely. Maven carries with it a package, a radio system, an Electra radio system developed at our Jet Propulsion Lab that can relay information from rovers such as Opportunity and Curiosity, even future rovers such as the rover we're designing for 2020, the Mars Caching Rover, or whatever we come to call it. In any event, so after it does its science, makes these fundamental measurements over a Mars year or perhaps extended, depending on what the people say, really. Maven can also serve another purpose as part of the infrastructure to let us get information back from Mars. And that infrastructure is critical. Without it, we could not return these gigabits a day from rovers like Curiosity and Opportunity that allow us to see what it sees so well.
That's interesting. And how long is the initial mission expected? Did you say a year?
The primary mission for the MAVEN investigation of Mars is designed to be 4 Mars seasons, about a Mars year. We really know we need at least an Earth year, which is sort of 2 Mars seasons. But Mars is a longer cycle around the sun, takes about 690 days. So we'd like to run it for that full Mars year, compare the seasons, what's changing, and then, with good fortune and great data, perhaps be permitted, through competitive peer review, to extend the mission another Mars year. That would be a wonderful state. But the primary mission is to look at Mars across its full seasonal cycle.
Great. And there are a lot of instruments being carried on MAVEN. And I'm curious if you wouldn't mind sort of telling me the broad strokes of what they'll investigate. I know some of them are looking at the sun.
Right. Well, MAVEN carries 3 kinds of experiments. There are classical remote sensing experiments that look through the atmosphere at the surface, at the atmosphere in cross-section, to measure chemistry, structure, and even aspects of how it's dynamic. We have other experiments that look at the particles and fields that stream from our sun, the so-called solar wind, the space weather, if you will, in part, driven by our big parent sun. We need to understand that at Mars so that we can then understand what we're measuring about the Mars atmosphere as it interacts with that at the same time. And that's critical. Simultaneous measurements, the action of the sun, the chemistry of the atmosphere. And then we have other experiments, one developed here at the Goddard Space Flight Center, that will measure using a technique known as mass spectrometry. I know it sounds mysterious, but we really weigh things really well, is kind of the trick that the team here has used, that will measure in situ, directly, the chemical constituents of that atmosphere that's being sloughed off or lost into space. So we have remote sensing, in situ sensing, and particles and field sensing, all in one mission. And that's really pretty amazing. It's a little reconnaissance climate satellite system for Mars.
Wow. And methane investigation is not part of that, correct?
Well, methane is one of dozens of trace gases that are really cool. I mean, they're small, they have a short lifetime. Methane, again, is one of many. And this mission is looking at the bigger picture. Other missions can target a single species. Curiosity has shown us the background for methane is very low, at least in Gale Crater, very different than was anticipated from some of the excellent Earth-based measurements and ones from orbit. But I think the story is bigger than that. And the trace gas orbiter that our friends from Europe and Russia will be launching in 2016 will attempt to fill in more gaps about other chemical constituents that are in trace amounts that will look for things beyond methane. We will connect that bigger atmospheric story through MAVEN to the surface of Curiosity, waiting for the other measurements by our friendly partner nations.
Great. And what bearing does the work MAVEN will be doing have on our understanding of even Earth's atmosphere or other planets?
Well, we think that comparisons, working by analogy, allows us to better inform how our own world works. And we've seen that ever since the first space missions, even when we looked at our first weather satellites of Earth in the 60s, when we brought back the samples from the moon, the first mission to Mars to ask, is Mars alive today? Viking. All informed how we would even tackle that problem here on Earth. And together, those have shown us that there are lessons from Mars that have already been applied to Earth, questions we wouldn't have asked about the evolution of our atmosphere, the role of colossal impacts, which we know have affected the record of the history of life on Earth. Without the space program, exploring other worlds such as Mars, those questions would have been posed differently. So by looking at ourselves as a planet in space, living in space, working in space, and comparing to Mars, to our sister planet Venus, to the moon as our natural satellite, to other worlds like Mercury, we start to get a picture of how this universe really works, how unique we are, where we could be going. And that's how we better predict destiny, understanding what's really happening in space to planets.
That's great. And then one final question. What do you think is the most surprising or even exciting fact about the MAVEN mission?
Well, to me, I think the hallmark of MAVEN is not only that it's a mission that we knew we needed to do in the 70s, literally, as recommended by many studies by the science community, that we're finally doing it, but that it was a competitively selected mission. That this is a mission that went through the Science Engineering Olympics to get to where it is today, nearly ready to launch on its journey to Mars. And that competitive edge, what makes athletes do well in the Olympics and sports, is the same in the engineering science field. And so this is the best of the best going to Mars. And that's exciting. We've chosen the best for the money to do this job, and they're going. So it's great thing to know.
That's wonderful. Well, thanks so much for chatting with me. I appreciate it.
Sure.